Let's continue to read the book Until the End of Time by Brian Greene. This is the second chapter, The Language of Time. And this is the third part, Laws of Thermodynamics. While entropy and the second law enjoy a great many cultural references, public nods to the first law of thermodynamics are less common. Yet to fully grasp the second law, it's good to grasp the first law first. As it turns out, the first law is widely known too, but under an alias. It's the law of energy conservation. Whatever energy you have at the beginning of a process is the same energy you will have at the end of the process. You must be fastidious in your energy accounting, including all forms into which an initial cache of energy may have transformed, such as kinetic energy, energy of motion, or potential energy, stored energy, as in a stretching spring, or radiation, energy carried by fields, like the electromagnetic or gravitational fields, or heat, the random jittery motion of molecules and atoms. But if you keep track carefully, the first law of thermodynamics ensures that the energy balance sheet will balance. The second law of thermodynamics focuses on entropy. Unlike the first law, the second is not a law of conservation. It is a law of growth. The second law declares that over time, there is an overwhelming tendency of entropy to increase. In colloquial terms, special configurations tend to evolve toward ordinary ones. Your carefully pressed shirt becomes creased and wrinkled, or order tends to descend into disorder. Your organized garage degenerates into a haphazard mess of tools, storage boxes, and sporting equipment. While this depiction provides a fine, intuitive imaginary, Boltzmann's statistical formulation of entropy allows us to describe the second law with precision and, just as important, gain a clear understanding of why it is true. It comes down to a numbers game. Consider again the pennies. If you carefully arrange the pennies so they are all heads, a low entropy configuration, and then subject them to a little shaking or jostling, you expect to get at least a few tails, a higher entropy configuration. If you shake them further, it is conceivable that you will get back to all heads. But that would require the jostling to be just right, to be so perfectly attuned that it flips back only those few coins that happened to be tails. That's extraordinarily improbable. It is fantastically more likely that the jostling will instead flip a random collection of the pennies. Some of the few coins that were tails might revert to heads, but of the coins that were heads, many more will become tails. So straightforward logic, no fancy math, no unduly abstract ideas, reveals that if you begin with all heads, random shaking will drive an increase in the number of tails, an increase that is of entropy. The progression toward a greater number of tails will continue until we reach a roughly 50-50 heads-tails split. At that point, the jostling will tend to flip about as many heads to tails as tails to heads. And so the pennies will spend most of their time migrating among the members of the most populous, highest entropy groups. What's true for the pennies is true more generally. Bake bread, and you can be sure that the aroma will shortly fill rooms far from the kitchen. At first, the molecules released as the bread bakes are clustered near the oven, but those molecules will gradually disperse. The reason, similar to our explanation with the pennies, is that there are many more ways for the aroma molecules to spread compared with ways for them to cluster. It is thus overwhelmingly more probable that through random bumping and jostling, the molecules will waft outward as opposed to clump inward. The low entropy configurations for molecules clustered near the oven thus naturally evolves towards the higher entropy state in which they are spread throughout your house. Saying it yet more generally, if a physical system is not already in the highest entropy state available, it is overwhelmingly likely that it will evolve toward it. The explanation, illustrated well by the breath aroma, rests on the most basic reasoning. Because the number of configurations with more entropy is enormously greater than those with less entropy. By the very definition of entropy, the odds are enormously larger than random jostling. The relentless bumping and vibrating of atoms and molecules will drive the system toward higher entropy, not lower. The progression will continue until we reach a configuration with our highest entropy available. From that point onward, the jostling will tend to drive the constituents to migrate among the typically gargantuan number of configurations of the highest entropy states. That's the second law of thermodynamics, and that's why it is true. That's the end of this section, but before I go on to the next section, I want to make a point about reading books. What kind of books you think have a higher entropy, and what kind of book have a lower kind of entropy? Of course, this is not precise, but I want to tell you the book that I'm reading right now, which is a physics book. It is difficult to read, it's difficult to understand, but it contains a lot of information. Contains a lot of important information. Is something that I would say with a lower entropy. It's more disciplined. It has information in it. It has, but of course this may not be right because information is equivalent to entropy. I don't want to confuse you on that, but I want to say because it is rare, this physics book is rare, so it has a lower entropy if you understand me well. But a popular book, a book about daily life, very usual. If you change the name, you would believe it would happen in another neighborhood, another family, etc. Is not rare. So it is a book of high entropy. To understand a book of high entropy, actually, it's not that difficult. That's why most people, without struggling, can read a popular book. But only a few people can read a book of physics, which has a low entropy, is a rare book. And it requires effort. Of course, for a physicist, it may not take that amount of effort to read it, but actually, because the physicist has already put years of effort. So that's why this book is very easy for it. But for a layman who do not know much about physics, it is so difficult to understand this because over the years they never put effort in it. They never put energy into it. So that's what I want to mention here. Okay, let's continue to read. The next section is entitled Energy and Entropy. The discussion might lead you to think that the first and the second laws are thoroughly distinct. After all, one focuses on energy and its observation, the other on entropy and its growth. But there is a deep connection between them, highlighting the fact implicit in the second law that we will return to repeatedly. All energy is not created equal. Consider as an example a stick of a dynamite. Because all the energy stored in the dynamite is contained in a tight, compact, orderly chemical package, the energy is easy to harness. Place the dynamite where you want its energy deposited and light the fuse, that is, post-explosion. That's it. Post-explosion, all of the dynamite's energy still exists. That's the first law in action. But because the dynamite's energy has been transformed into the rapid and chaotic motion of widely dispersed particles, harnessing the energy is now extremely difficult. So, although the total amount of energy doesn't change, the character of the energy does. Before the explosion, we say that the dynamite's energy is high quality. It's concentrated and easy to access. After the explosion, we say that the energy is low quality. It's spread out and difficult to utilize. And since the exploding dynamite fully abides by the second law, going from order to disorder, from low entropy to high entropy, we associate low entropy with high quality energy and high entropy with low quality energy. Yes, I know. It's a lot of highs and lows to keep track of. But the conclusion is a pity. Whereas the first law of thermodynamics declares that the quantity of energy is conserved over time, the second law declares that the quality of that energy deteriorates over time. Why then is the future different from the past? The answer, apparent from what we have now developed, is that the energy powering the future is of a lower quality than that powering the past. The future has a higher entropy than the past. Or at least that's what Boltzmann proposed. Boltzmann and the Big Bang, that's the next section. Boltzmann was surely onto something, but there is a subtle clarification to the second law, whose implications, truth to be told, took some time even for Boltzmann to appreciate fully. The second law is not a law in the traditional sense. The second law does not absolutely preclude entropy from decreasing. It declares only that such a decrease is unlikely. For the pennies, we have quantified this. Compared with the soul configuration with all heads, it is 100 billion times more likely that a random shaking will yield a configuration with 50 heads and 50 tails. Shake that high entropy configuration again, and getting a lower entropy configuration, such as all heads, is not forbidden. But because of the highly skilled arts, in practice, it doesn't happen. For an everyday physical system made from far more than 100 constituents, the odds against entropy decreasing become all the more daunting. As bread bakes, it releases billions upon billions of molecules, configurations in which those molecules spread throughout your home are spectacularly more numerous than those in which they collectively stream back toward the oven. Through their random jostling and bumping, the molecules could retrace their steps, find their way back to the loaf, fully undo the cooking process, and leave you with a mold of a cold raw dough. But the odds of that happening are closer to zero than the likelihood of a splattering paint on a canvas and replicating the Mona Lisa. Even so, the point is that were such an entropy reversing process to happen, it would not contravene the laws of physics. While spectacularly unlikely, the laws of physics do allow entropy to go down. Don't get me wrong, I'm not bringing this up to suggest we might one day uncook bread or witness a car uncrash or see a document unborn. Instead, I'm stressing an important point of a principle. I explained earlier that the laws of physics put the future and the past on equal footing. The laws that ensure that the physical processes that unfold in one temporal sequence can unfold in reverse. And since those very same laws govern everything, including the physical process responsible for how entropy changes over time, it would indeed be curious, erroneous really, to find that those laws only allow entropy to increase. They don't. All the entropically increasing processes you have experienced day in, day out during your entire life, from the mundane of a shattering glass to the profound of a bodily aging, can happen in reverse. Entropy can decrease. It's just ridiculously unlikely. So where does this leave our quest to explain why the future is different from the past? Well, given a configuration today of a less than maximum entropy, the second law shows that the future is overwhelmingly likely to be different because entropy is overwhelmingly likely to increase. Configurations of matter that have less than the maximum possible entropy are chopping at the bait to proceed to higher entropy. And with that observation, some exploring the differences between past and future rest easy, reckoning that their work is done. But the work is not done. Just as importantly, we need to explain how it is that we find ourselves today in such a special, unlikely, surprising state of less than maximum entropy, a universe replete with orderly structures from planets and stars to peacocks and people. Had that not been the case, had today's configuration been the expected, ordinary surprising state of maximum entropy, then with great odds, the universe would continue to inhabit such a state, yielding a future no different from the past, like a band of pennies jostling through the enormous number of configurations with roughly 50 heads and 50 tails. The universe would relentlessly meander through the enormous landscape of its highest entropy configurations, widely dispersed particles streaming this way and that across space, a cosmic version of you uniformly steam-filled bathroom. Today's state of less than maximum entropy is, luckily for us, far more interesting. It provides the opportunity for particles to join into structures and for macroscopic change to occur. And so we are led to ask, how did today's less than maximum entropy state come to be? Dutifully following the second law, we concluded that today's state derives from yesterday's even lower entropy state, and that state we envision derives from the day before yesterday's still lower entropy state, and so on, yielding a trail of ever-decreasing entropy, taking us ever farther back in time until we finally reach the Big Bang, a highly ordered, exceedingly low entropy starting point. At the Big Bang is why today's universe is not entropically maxed out, allowing for the eventful future that differs from the past. Can we go further and explain why the beginning of the universe was so ordered? We will come back to this question in the next chapter, where we will explore cosmological theorizing. For now, we note that our survival requires order. From our internal molecular organization, supporting a wealth of life-sustaining functions, to the food sources that provide us with high-quality energy, to the crafted tools and habitats that are essential for our continued existence. Without an environment choke full of low-energy, ordered structures, we humans would not be here to notice. Next section, heat and entropy. I began this chapter with Bertrand Russell lamenting a universe subject to relentless decline. With the second law of declaration of rising entropy, we have now caught a glimpse of what inspired this dark prophecy. Think of rising entropy as an increasing disorder, and you have the gist of it. But to fully appreciate the future challenges that will face life, mind, and matter, a theme we will amply explore in subsequent chapters, we need to establish a link between the modern description of the second law of thermodynamics, as I have laid it out, and the original formulation developed in the mid-1800s. In that earlier version, the second law codified what was obvious to anyone working with steam engines. The process of burning fuel to run a machine always produces heat and waste, degradation. However, as the earlier version made no mention of counting configurations of particles and made no use of probabilistic reasoning, it might seem a world away from the statistical statement of entropic growth that we have been developing. But there is a deep and direct connection between the two formulations, one that reveals why the steam engine's conversion of a high-quality energy into low-quality heat is illustrative of a ubiquitous degradation taking place throughout the cosmos. I will explain the link in two steps. First, let's look at the relationship between entropy and heat. Then, in the next section, we will tie together heat and the statistical statement of the second law. Grab hold of a saute pan's hot handle, and it feels like heat is flowing into your hand. But does anything actually flow? There was a time long ago when scientists thought the answer was yes. They envisioned a fluid-like substance called a caloric, which would flow from hotter locations to cooler ones, much like a river flows from upstream to downstream. In time, the more refined understanding of a matter's ingredients provided a different description. When you grasp the pen's handle, its fast-moving molecules collide with the slower-moving molecules in your hand, on average causing the speed of those in your hand to go up and those in the handle to go down. You sense the increased speed of the molecules in your hand as it warms. The temperature of your hand has increased. Correspondingly, the slower speed of the molecules in the handle means its temperature has decreased. What flows then is not a substance. The molecules in the handle stay in the handle, and those in your hand stay in your hand. Instead, much as information flows from one person to the next in a game of a telephone, molecular agitation flows from molecules in the handle to those in your hand when you grab it. And so, whereas matter itself does not flow from handle to hand, a quality of a matter, average molecular speed does. That is what we mean by the flow of a heat. The same description applies to entropy. As the temperature of your hand increases, its molecules bounce around more quickly. The range of their possible speeds widens, increasing the number of attainable configurations that pretty much look the same, and so the entropy of your hand increases too. Correspondingly, as the temperature of the handle decreases, its molecules move slowly. The range of their possible speeds narrows, decreasing the number of attainable configurations that pretty much look the same, and so the entropy of the hand decreases. Wow, entropy decreases. Yes, but this has nothing to do with rare statistical flukes like dumping a bag of pennies and getting all heads. As described in the previous section, the entropy of the hot handle will decrease every time you grab it. The simple yet vital point the salty pen illustrates is that the second law of a dictum of entropy increase refers to the total entropy of a complete physical system, which necessarily includes everything with which the system interacts. Since your hand interacts with the pen's handle, you cannot apply the second law to the handle on its own. You must include both the handle and your hand, and to be more precise, the entire pen, the stove, the surrounding air, and so on. And a careful accounting shows that the increase in the entropy of your hand outstrips the decrease in the entropy of the handle, ensuring that the total entropy does indeed go up. So much as with heat, there is a sense in which entropy can flow. For the pen, it flows from the handle to your hand. The handle becomes a little more ordered, and your hand becomes a little less ordered. Again, the flow is not in the form of a tangible substance that was initially in the handle and has now moved to your hand. Rather, the entropy flow denotes an interaction between the molecules in the handle and those in your hand that affects the properties of both. In this case, it changes their average speeds, their respective temperature, and that in turn affects the entropy they each contain. As the description makes manifest, the flow of heat and the flow of entropy are intimately connected. To absorb heat is to absorb energy that is carried by random molecular motion. That energy, in turn, drives the receiving molecules to move more quickly or spread more widely, thus contributing to an increase in entropy. The conclusion, then, is that to shift entropy from here to there, heat needs to flow from here to there. And when heat flows from here to there, entropy shifts from here to there. In short, entropy rides the wave of a flowing heat. With this understanding of the interrelationship between heat and entropy, let's now revisit the second law. Next section, heat and the second law of thermodynamics. Explaining why we experience events unfurling in one direction but not the reverse brought us to Boltzmann and his statistical version of the second law. Entropy is overwhelmingly likely to increase toward the future, making reverse run sequences in which entropy would decrease fantastically improbable. How does this relate to the earlier formulation of the second law, inspired by the steam engine, which was phrased in terms of relentless production of waste heat by physical systems? The connection is that the two starting points, reversibility and the steam engines, are tightly linked. The reason is that the steam engine relies on a cyclical process. A piston is thrust forward by expanding steam and is then reset to its original position, where it awaits the next thrust. The steam, too, reverts to its original volume, temperature, and pressure. As much all of the engine's vital parts, readying the engine to heat back up and thrust the piston once again. Well, none of this requires the ridiculously improbable unfolding in which every molecule finds its way back to exactly the same spot or acquires exactly the same speed as it had at the start of the previous cycle. It does require that the overall arrangement, the engine's macrostate, returns to the same form to initiate such a subsequent cycle. What does that imply for entropy? Well, since entropy is a count of the microscopic configurations that presents at the same macro state, if the macro state of the steam engine is reset at the start of each new cycle, then its entropy must be reset too, which means that the entropy the steam engine requires during a given cycle, as it absorbs heat from the burning fuel, as it generates additional heat through friction of its moving parts, and so on, must all be expelled to the environment by the time the cycle concludes. How does the steam engine accomplish this? Well, we have seen that the transfer entropy, you must transfer heat. Thus, for the steam engine to reset itself for the next cycle, it must release heat into the environment. That's the historical statement of the second law of thermodynamics. The inevitable expunging of waste heat into the environment, the very degradation that so weighed on Bertrand Russell, now derived from the statistical version of the second law. This is the destination I have been heading for, so feel free to jump to the next section. But if you have the patience, there is one detail I would be remiss not to mention. You might wonder, if the steam engine absorbs heat from the burning fuel, thus absorbing entropy, only to release heat to the environment, thus releasing entropy, how does it have any remaining energy to accomplish useful tasks, like powering a locomotive? The answer is that the steam engine releases less heat than it absorbs, and yet is still able to fully punch the entropy it has built up. Here's how it goes. The steam engine absorbs heat and entropy from the burning fuel and releases heat and entropy to the cooler environment. The temperature difference between the fuel and the environment is what's vital. To see why, imagine turning on two identical heaters, two identical space heaters, one in a room that's frigid and the other in a room that is hot. In the frigid room, the cold molecules of air are jolted by the space heater, causing them to move faster and disperse widely. And so their entropy increases significantly. In a hot room, the air molecules are already moving fast and fleeting widely. And so the space heater only slightly increases their entropy. It is kind of like turning up to the beat at a wild New York's party and barely noticing that the revelers dance a touch more quickly, but turn up the heat at the Dinksey monastery, enticing monks to break from their meditative practice and start cramping, and you would readily see the change. So even though the two space heaters are identical, the entropy they transfer to their surroundings is different. While each generates the same amount of heat, the space heater in the cooler environment transforms more entropy. A cooler environment thus amplifies a given amount of heat received into a larger entropy increase. With that realization, we see that the steam engine can discharge all of the entropy it acquires from the hotter fuel by expelling only part of that heat to the cooler environment. The remaining heat is then available to drive the steam to expand, pushing the piston and accomplishing useful work. That's the explanation, but it does let the details cloud the larger conclusion. Over time, physical systems will, with a fantastic likelihood, evolve from configurations of lower entropy toward configurations of higher entropy. If a system, like a steam engine, seeks to maintain its structural integrity, it must stave off of the natural drive toward increased entropy by transferring the entropy it builds up to its surroundings. To do so, the engine must release waste heat to the environment. The next section, entropic two steps. If you carefully think through the steps we have followed, you will see that although the steam engine has been peppered throughout, our conclusions transcend this 18th century starting point. The essence of our analysis is a close accounting of entropy, and the accounting can be carried out in any context. This is a key realization because the shifting of energy from the steam engine to its surroundings through the release of heat is but one version of an utterly ubiquitous process we still encounter as we follow the unfolding of the cosmos. I call it the entropic two-step, by which I mean any process in which the entropy of a system decreases because it shifts a more than compensating increase in entropy to the environment. The two steps ensures that even though the entropy may decrease here and it will increase there, securing the net entropic increase we expect based on the second law. The entropic two-step lies at the heart of how a universe heading toward ever greater disorder can nevertheless yield and support ordered structures like stars, planets, and people. A theme we will encounter repeatedly is that when energy flows through a system, like the energy from burning coal flowing through the steam, driving work, and then existing to the surrounding environment, it carries away entropy and can thus sustain or even produce order in its wake. It is this entropic dance that will choreograph the rise of life and the mind, as well as most everything that minds deem to matter. The next section, you are a steam engine. With the importance of resetting the entropy each time a steam engine goes through a cycle, you might wonder what would happen if the entropy reset were to fail. That's a tantamount to the steam engine not expelling adequate waste heat. And so with each cycle, the engine would get hotter until it would overheat and break down. If a steam engine were to suffer such a fate, it might prove inconvenient, but assuming there were no injuries, would likely not drive anyone into an existential crisis. Yet the very same physics is essential to whether life and mind can persist indefinitely far into the future. The reason is that what holds for the steam engine holds for you. It is likely that you don't consider yourself to be a steam engine or perhaps even a physical contraption. I, too, only rarely use those terms to describe myself. But think about it. Your life involves processes no less cyclical than those of the steam engine. Day after day, your body burns the food you eat and the air you breathe to provide energy for your internal workings and your external activities. Even the very act of thinking, molecule motion taking place in your brain, is powered by these energy conversion processes. And so, much like the steam engine, you could not survive without resetting your entropy by purging excess waste heat to the environment. Indeed, that's what you do. That's what we all do. All the time is why, for example, the military's infrared goggles designed to see the heat we all continually expel do a good job of helping soldiers spot enemy combatants at night. We can now appreciate more fully Russell's mindset when imagining the far future. We are all waging a relentless battle to resist the persistent accumulation of waste, the unstoppable rise of entropy. For us to survive, the environment must absorb and carry away all the waste, all the entropy we generate, which raises the question, does the environment, by which we now mean the observable universe, provide a bottomless pit for absorbing such waste? Can life dance the entropic two-step indefinitely? Or might there come a time when the universe is, in effect, stuffed and so is unable to absorb the waste heat generated by the very activities that define us, bringing an end to life and mind? In the lachrymose phrasing of Russell, is it true that all the labors of the ages, all the devotion, all the inspiration, all the noonday brightness of a human genius are destined to extinction in the vast depth of the solar system, and that the whole temple of a man's achievement must inevitably be buried beneath the debris of a universe in ruins? These are among the central questions we will explore in coming chapters. But we have jumped a little ahead of ourselves. Before we discuss life and mind, let's understand how entropy and the second law play out in the formation of environments necessary for life and mind to take hold. For that, we head back to the Big Bang. That's the end of chapter 2, and I just want to make a very quick comment here. That is, no matter how Rousseau was saying about the darkness in the end of the universe, it is nothing new, because we all faced death in our lifetime. That itself is the dark age for ourselves. So we already know that. So what's new about that? Nothing new about that. The wonder of this universe, the wonder of these physical laws, the wonder of entropy itself, all these laws, beautiful laws, have told us that it is worth living, and we thank God for that, for the Creator to have all these things for us.